strengthen the structure when they grow this fancy fin that they have. So you can classify them as ionic because clearly sodium chloride, you have a cation, anion, and they go into lattice, lattice, BCC lattice that intertwine with each other. And then you have covalent materials such as carbon, like diamond, phosphor, silicon dioxide, gallium arsenide, and so forth. And of course, then you have metallic solid, which we talk about in terms of the metallic bonding. Metallic bonding is the strongest bond, right? It's the strongest bond in nature. Metallic bonding can be thought of as just a bunch of nuclei, right? What is a metallic bond? You can think of this as a bunch of nuclei, right? Positive core, surrounded by a sea of electrons. So this is your metallic bonding that you have. And that's why it's so strong, is that you don't have, unlike the covalent bond that you have, which we could think of most solid material, they are hard to pull apart because they have held together by not just one electron share in the orbital, but a bunch of electrons in a sea, in this sea of electrons that you see. Okay, so that's chemists would like to classify them based on bonding between atomic center, and that's another way of this. And of course, you could be very complicated. You can go into complex solid, which have different type of material, cadmium sulfide, cadmium cyanide. These are quantum dot material, 2,6 material that generate quantum dot. That very exciting work has been going on the last 10 years of this quantum dot material, and they have complex. They are classified complex solid because they have a binary solid involving different type of bonding, both ionic and covalent bonding. Okay, so this is just a brief introduction to these physical property of this material that you see. What I want to do next is to tell you a little bit about a little bit deeper about the origin of this band gap, right? Band gap, so I say origin of the band gap and band structure is solid. So we want to first look at qualitative consideration from something we know as chemists, simple MO theory, right? So we're going to use MO theory to learn a little bit about how do we build from MO theory this band gap, can we generate band gap and band structure of a solid on this. So what is MO theory? Well, we think of chemical bonding of molecule and solid in terms of orbitals, right? So this is how we think. Unlike the physicists, they like to think in terms of potential forces rather than us. We like to think in terms of wave function and orbitals. One electron wave function is an orbital, and we can distinguish between the core atomic orbital, which are deep, very close to the nuclei. They are held tightly by the nuclei. They do not involve in any kind of interaction with the neighbors. And the neighbor interaction, those ones are called valence orbitals, right? They are way out, very far away from the positive nuclei of your atoms, and they can interact with the other one. They are diffuse, spatially diffuse atomic orbitals that you have. And the core, deep down close to the nuclear core and atomic light, they have little or no bonding influence, whereas the valence orbital, of course, have large spatial extent, and these wave functions overlap with one another, creating these molecular orbitals. Okay? And there are three types, as we know, bonding, most stable, non-bonding, not so stable, and anti-bonding, less stable, even less stable than that. So here we have, very quickly we can write, in first year chemistry, we learn about this molecular orbital theory. And molecular orbital theory is essentially this LCAO MO theory, linear combination of atomic orbitals to make MO, right? So you start off with psi 1 and psi 2, and chi A and chi B are your atomic orbital some coefficient. You either add them or you subtract them. You add them in sync with phase or anti-phase. So think of this: the chi is a hydrogen 1s orbital, right, of the hydrogen atom. So you can either add them in phase or anti-phase, right? You can combine them coherently or incoherently. That's another way to think about it. So we now have, we can then create it, of course, when you combine them, you would have bonding orbitals. So let me draw a picture. So you have 1s here, another 1s here, right? You combine them, you add them, and what you get is, of course, like this, right? That will be what we call 1 sigma G orbital, right? And for H2, this is H2, and this is hydrogen atom like this. And of course, you can subtract them, right? You can also subtract them, and what do you get? When you overlap them, subtract them, you would have like this. You remember in first year chemistry, this is a 1 sigma U orbital, ungerade, or 1 sigma U, or sometimes it's called 1 sigma U star. Right? Star indicating its anti-bonding orbital like this. And you have a nodal plane, and this orbital has higher energy than this one. And this is, of course, the HOMO, and this is the LUMO in the case of H2 molecule like this. Right? This is simple MO theory that we learned in first year chemistry. Okay, so we have, and of course, in some cases we have a non-bonding orbital as well. You have orbital like in water, for example. Remember we were talking about water in the X-ray for the emission spectra there, and the 1b1 orbital is the non-bonding orbital that it doesn't involve another site. It just itself is not bonding, it's not sharing its electron with the neighbor atom. So that is known as a non-bonding orbital in addition to this combination either on its own in a positive way or negative way. Okay? And the key point is that the number of MO depends on the number of AO used to make them, right? So if I start off with 2 AOs, I should get 2 MOs because I have 2 different ways of combining them. And that is the key point, is that now if you imagine that you increase the number of AO, you can imagine that the number of MO that I would get will increase dramatically. And of course, each MO lies at a different energy, and this leads to energy band structures. So here's a simple way of explaining these things, like here, right? So here we draw my picture like this. You have 1s, 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 1s. So I would have, here I'm trying to make my diatomic molecule, right? This is my diatomic molecule. I have my, this is the MO diagram. I hope people still remember how to do MO diagram. I have 1 electron in the hydrogen 1s orbital and another one here. I combine them to make H2 molecule, and this is my 1 sigma orbital and 1 sigma star orbital. So when you combine them, why you make molecule? Why molecule stable? Well, because when you combine this way, you create an energy level that's lower than any of these 2, right? That's lower than the hydrogen 1s orbital. And so that's why you created a more stable situation than a separate entity. If they're separate, they have higher energy than this, right? So therefore, you can make a molecule, a new entity, by combining them because you get a lower energy, right? So now you put them together into the 1 sigma orbital, and you have this MO diagram that you have. And this is a cross section of the psi 1 orbital, the bonding orbital, and this is of the anti-bonding orbital, which is what we see here. This is, of course, the nodal plane that we have. And you see accumulation of electrons, right, between the atomic center in here once you form the sigma orbital like this. Right, and then what happened next? You can also form like NO or CO. In the case of hydrogen, of course, you're combining identical material, they would have identical energy level. But you're looking at nitrogen and oxygen, for example, their energy level would be different, right? So you would have a set of energy level here and a set of energy level here, and they're not the same to each other. So when you combine them, you combine it in this way. You have asymmetry, you have certain atomic center, we have higher